Okay, howdy gang. We're going to do a shear moment diagram problem for you here today, and I'm going to put a little extra on here. This one has a moment on it. You'll notice it has a concentrated moment on the load curve. So we'll have to talk about how to handle that moment. It's a little bit special, okay? So the problem statement here says draw the shear moment diagram for the following load curve. So I've got this load here. It's a cantilevered beam, so we have a fixed support over here. And we're going to have to draw a shear moment diagram for that. So I'm going to just draw a line here. Okay, my pen quit writing there. Okay, and it's good when you do these to have plenty of room on your paper so that you can kind of do these in order, because this curve is related to that curve, this curve is related to that curve, right? This one's the integral of the next. This is the integral of that curve. This is the integral of that curve. Okay, so I'm going to call this the load curve. Okay, this is going to be V. Remember the shear is V. And this is going to be our moment diagram down here. And the shear diagram for this one is going to be in, remember, it's shear force. And so the force here is going to be in kips. You remember what a kip is? Remember, it's a kilopound, 1,000 pounds, okay? So this is going to be in kips, and this one's going to be in foot kips. So I'm not going to put any units on my graph, but that's the units for each of those curves. Also, I have drawn this. I've been over this before, but here we go again. We talk about the order of the lines, okay? So if I have one graph that has a concentrated load on it, like this is a concentrated load, right? My graph will go straight down. The next graph down from the concentrated load will be a constant, just like an x equals 5, just straight across. What's the integral of a constant? Well, you put an x with it. What's the integral of an x? It's an x squared. What's the integral of an x squared? It's an x cubed, right? So I have a cubic, a square, a sloped line, a constant line, and a concentrated load. So those are, if I know what I have on one graph, like this is a constant, so the next graph down from that will be a sloped line, right? Okay, so step one for this process here, and we're going to use the graphic method on this, but as always, we need to find global equilibrium. Okay, so finding global equilibrium here, I've got three things. This fixed support has three reactions, if you recall. It has, I don't know, maybe an AY, an AX, and then it has all this stuff is trying to rotate it down, so I think it has a moment like that. We'll call that the moment at A. Okay, so I have those three reactions over there. I need to find those. Well, do we see any forces in the x direction? I don't see any, so AX must be 0, okay? So, remember, when we have a concentrated load, we can turn that into a distributed load, okay? So I've got 2 kips per feet times 6 feet of it, so that's 12 kips. Now, here's a little clue, okay? You only use the concentrated load to find global equilibrium. After that, you have to put it back to a distributed load, because a distributed load is graphed different than a concentrated load. Okay, so we definitely have a distributed load. We need to keep it there. Okay, so here we go. Let's take the I don't know. Let's take the moment at A. Okay. Well, what does AY have to be, y'all? How much downward force do I have? I've got 12 there and 10 there, and then 8 there. So 8 and 12 is 20, plus 10 is 30. So AY has to be 30. If I've got 30 going down, I've got to have 30 going up, don't I? Okay, so 30 kips. And we need to find that MA. Okay, so let's do this. Let's take the sum of the moments at A. Okay, this being positive. Okay, we drew MA as a positive, so MA. And then the 12 is rotating me clockwise, so that's minus 12 times, how far away is the 12? How far away is this? Well, it's half of 6, so it's 3. Okay, and then I've got the 10 also rotating me negative, minus 10 times it's 6 away. And then I've got 8 over here, so minus 8 times how far away is that? That's 10, 6 plus 4. And then I've got this burrito force over here on the end, right? That's just a negative moment, so just minus 40, right? So I just need to add all that stuff up since it's all equal to 0 and move all this to the other side, right? So here we go on. 12 times 3 plus 60 plus 80 plus 40 is 216. Okay, so MA is 216 foot kips, okay? So we'll use that here in a minute. Okay, we'll use that down here on the M graph. Okay, so let's do the V graph, okay? So we're going to use the graphic method for this, okay? So again, think about that you have a load backpack, right? And it's empty. And as you step on the beam, I'm going to start putting stuff in your backpack, okay? So as soon as you step on the beam, what's the first thing that I'm going to give you? 30 kips going up, right? So right as soon as you get on here, then you're going to be up here at 30, right? Now, as you take a step, I put 2 kips per foot in there. So take a foot step, put 2 kips in. Take another foot, 2 more kips. Another foot, 2 more kips, right? So you're going down 2 at a time over 6, so you're going to go down 12. So at this point, we'll put a little dash line here. I'm going to put a dash line everywhere I think something interesting is going to happen, okay? And I'm going to go from here down to here. I'm going to go down how far? Well, 2 at a time for 6 steps. So I'm going to go down 12. I'm at 30, so that's going to take me over here to 18, right? Okay, so now I'm at 18 there. Now look, a concentrated load. What does a concentrated load do? It makes you jump straight up or down on your graph. This one's down, so I'm going to jump down 10. Whoop. Now I was at 18, so now where am I? Whoa, I'm not that far down, am I? Because I'm at 18, so I only went down 10. So maybe I'm there. I'm at 8 now, right? Now, how much force do I get? What's the change in force across here? Well, nothing, no change, no change, no change, no change, until I hit this, and there's 8. Well, I'm at 8, and so, boom, drop back down to 0. Okay, so there is my shear graph. Okay, now doing the graphic method, one of the things that you can do here is you want to divide this up into shapes. So I'm going to just put a line across there, right? Because this shape here is a triangle that's on top of a rectangle, okay? Now I'm just going to write the areas on here. Let me get a different color marker. Oh, there's my blue one. Okay, so the area of this guy is what? Well, it's 8 tall by 4 feet wide. And 8 is in kips and 4 is in foot, so the area of that is what? Foot kips. That's right, that's a moment, isn't it? So 8 times 4, 32. Okay, and the area of this guy, the rectangle, is 6 times what? Times 18, right? 6 times 18. What is 6 times 18? 6 times 18 is 108. Okay, that's 108. And then this portion here, the triangular portion, is 1/2. The base is 6. The height is 12. Okay, so that's what, half of 6 is 3, and 3 times 12 is 36, right? So this is 36. So the total area of this thing here is what? 108 plus 36 is 144, right? So the area of this thing total is 144. Okay, I put a circle around that and a circle around that. Okay, so here we go. So all I've done so far is just taken the area of my graph here, okay? Now, we need to talk real quick about moments. So I've got a moment here, and I've got a moment here. So I've got one at the start of the beam and one at the end of the beam. Remember, you always work these shear moment diagrams from the left to the right, okay? You can think of moments bending a beam 2 different ways. One like this, and one like that. So let's put my little moments on here, okay? All right, And I was looking for my, I don't know where it is. Okay. Well, we can do it with this, right? So here's my eraser. So the top one is I have a moment that's curling this way, and it makes that beam want to do like that, right? Look at the top of that. It's wrinkled, isn't it? It's because it's in compression, and the bottom down here, these fibers are being stretched apart. It's in tension. Consequently, if I go the other way, right, it goes like that, okay? So those are the two kind of beam bending that you can get out of a beam here, around the z-axis in this case. But how do I know the signs for this? What are we going to call this? Well, when you're doing a shear moment diagram, this is a positive bending, this is a negative bending. In other words, it's going to move you, this side is going to move you up the graph, this side will move you down the graph. This one will move you down the graph over here, but back up the graph over here, right? Because if I have a moment, the sum of the moments is 0, so whatever I go down, I've got to come back up, okay? Now, one way you can kind of remember this is that looks like a smile, doesn't it? And smiles bring you up, right? But frowns bring you down. There's the down arrow, okay? But another way that I think the best way to think about this, let's look at this. On our graph, when we're talking about our graph, if you have a clockwise moment, it's positive. Look, what is this one over here? Right, this is negative, positive. This is clockwise. So no matter where it is, clockwise is always going to take you up the graph. Counterclockwise, like this or like that, counterclockwise is always going to take you down the graph, okay? So over here I have what? A counterclockwise moment, so that's going to go down the graph. And over here I have what? A clockwise moment, that one's going to bring me up the graph, okay? So this is what you need to remember right here when you're graphing these, okay? So let's see if we can graph this. So the first thing we come to over here, now on the moment graph, that's when our moments are going to come in. Notice we didn't do anything with this moment on the V graph. It's because moments go in the moment graph, okay? So the first thing I do is I hit this moment at A. And how big was that moment at A? Well, it was 216 foot kips. So we just said that that guy is counterclockwise, so we're going to go down the graph, 216, okay? So here I go down, and there I am at 216, okay? Now, how am I going to come back up the graph? Because I have to come up the graph, how far? Well, I'm going to use this area here to tell me how far up the graph I'm going to come. So I'm going to come back up 144, because remember, that's foot kips, okay? And here's something you can remember. When on your V graph, if you have a positive area, you're going to have a positive slope on your M. If you have a negative area, you're going to have a negative slope. But here we have positive and positive. So I know I'm going to come uphill, and then I'm going to come uphill some more, aren't I? Okay? So I'm going to go up from 216, I'm going to come up 144. So where is my calculator? So I'm at 216, right? 216, whoa, clear. 216 minus 144 is going to take me up to 72. Okay, so there's 72 right there. So the question I have for you is, how do I get from the 216 to the 72? Well, I know that this is a slope, right? In my order of the lines, if I'm on slope, what's the next one going to be? A parabola, right? A parabolic function. But I have choices, right? The parabola can go like this, or it can go like that. Well, that's kind of good, isn't it? Okay, so which one is it? Now, what do I call this? I call this fast, then slow. Think about the slope of the line. Think about a ski slope, right? Wouldn't a fast slope be real steep? Okay, and what I'm thinking about is the rate that I accumulate this load. If I take one step over here, I'm accumulating a tall stack. If I take that same step over here, I'm just accumulating a short stack, right? So this curve needs to go fast, then slow. Which one of these goes fast and slow? That one is slow, then fast at the end. But this one is fast and slow, isn't it? So that's the correct one, okay? So our curve looks like that. Concave like that. And that's the biggest mistake students make, is which way do I draw my concavity there, okay? Okay, and now we're on to the next one, which is here. Now I'm going to come up 32. Now I'm at 72. So if I come up 32, where's that going to bring me to? let's call it 40, right? If I come up 32, I'm going to be at 40, but how do I get from there to there? Well, this is flat, right? Here's flat, constant, so the next line down is going to be a slope, right? So it's going to be a straight slope. Look how straight that is. Okay, we didn't come out to 0. We have to come out to 0. Wait a minute, look, there's a moment that's 40. And remember, that's clockwise, and clockwise is going to take us up the graph. So, boom, takes me back to 0. You have to get back to 0 on both these graphs. That's a good check steps for you. If you don't get back to 0, you know you've messed up, right? So there is my moment diagram. So now I could ask you some questions about that graph, like, what is the biggest moment on this whole beam, the biggest bending moment on the whole beam? And where is it? Well, the biggest bending moment is 216 foot kips, and it's over there at the wall, isn't it? What about if I asked you what's the biggest shear force on the beam? Well, it would be 30. Again, it's right there at the wall. Then I could ask you, like, what's the shear force at, I don't know, 8 feet, which is like right in here, right? Well, I just go down here and read it off my graph. The shear force at 8 feet, well, it's 8 tall all the way across here, right? That's 8 kips. So it's 8 kips at 8 feet, right? So I can tell a lot of things about what's going on in my beam from these diagrams. Okay? There you go. I hope that helped, and we'll see you next time.